I'm going to do these horse and cart problems here. Let's see what we got. Got a horse, a cart, a guy. Horse pulling a cart, accelerating the cart forward. So not constant velocity. That means the forces in the direction of motion are not balanced. If it's accelerating the cart forward, that means there's got to be some extra force in the forward direction. We don't know how much, but we know that there's got to be at least some extra in the forward direction. So if that's a news flash to you right now, you should probably pause this and see how you think that might affect your diagrams. All right, so number one, draw and label a force diagram for the cart to the left of the picture. And the horse to the right of the picture. That makes sense because that's where they are. I shouldn't have scribbled on there. And we're going to add quantitative values. That means quantitative means numbers for as many of the forces as possible. And we know how to do some of that now because of our force of gravity stuff, right? Okay. And also we know that we've got some masses here, and we're just being told the horse pulls on the cart with a force of 75 newtons. Okay, so cart. Force of gravity on the cart from the entire Earth. And now I can say that is equal to, remember that to find that horse, the horse of gravity. That's funny. The horse, the force, what's the source of the force on the horse? That's, we'll get to that in a minute. The force of gravity is, for the cart and rider, we take the mass and we multiply by 10. And units of force are newtons. Now, this cart is not moving in the up-down direction. So we know that the forces in the up-down direction are balanced. So that normal force on the cart from the ground is also going to be 1,500 newtons. I mean, I made tick marks here, but if we know the numbers, we're going to put them in the diagram there. And then I know that there is a force of pull on the cart from the horse. And we don't know anything about, we are going to talk about friction, so we're not ignoring that. So there's some friction force here, but it's not as big as this. How do I know that? Because the cart's accelerating forward, so there has to be some extra force. There doesn't have to be like a whole extra force, like two of them in this direction, one. We just have to have more, a more bigger number. And we know that the horse pulls on the cart with a force of 75, so we actually know this because we were just given that. 75 newtons. And then here's the force of friction on the cart that's going to be from different stuff. There's going to be some friction in here. So, I don't know. Let's just say stuff. That seems like horribly sloppy, whatever. We don't know exactly, it's a little bit too hard to describe. The friction, it's not the wheels here because this isn't being like dragged, like scraping along the ground. It's not that kind of friction. The friction is going to come from the axle and stuff like that. So, let's see. I'm going to ignore that phone call. Hold on one sec. Sorry about that, folks. I just wanted to see who it was on the caller ID so I can call them back. But they're not going to get in the way of our physics, of our horse and cart. Okay, so all I know is this is bigger than this, so I don't have a number for this. Okay, how about the horse? Got the force of gravity on the horse from the entire Earth, and I think we can put a number on that because the horse has a mass of 230, so I'm going to multiply that by 10, slap a 0 on there. And horse is not moving in the up-down direction, so I know that the support force, or the normal force, on the horse from the ground is going to be equal to that. And so I'm going to go ahead and do this. I'm not going to use 1 because I already used 1 over here. I'm not going to fuss at you too much if you make that mistake, but just for clarity, I don't want somebody who's looking at these diagrams to think that this is equal to this. So this is also 2,300 newtons. And let's see. If this is the important Newton's third law thing here is anytime in physics class that you find yourself making 2 force diagrams, or maybe more, for 2 things that are interacting with each other, there's going to be a Newton's third law pair. In other words, that equal opposite, like what are the 2 things that are interacting here? The cart and the horse. So if this is a force of pull on the cart from the horse, then there's a force of pull on the horse from the cart, because there's only one horse cart, that's my hands pulling on each other, right? There's only one horse cart interaction there, and it's not possible for them to be equal to different numbers, because there's only one force. The force is that interaction. So if you got a 75 here, force of pull on the cart from the horse, force of pull on the horse from the cart, and those are equal to each other. So I think I'm up to 3 now. It's my next available number of marks there. And then there's got to be something here that's bigger since we are accelerating forward. I can make sure that looks bigger. This is the force. Let's see, what do you want to call this? This is like the horse, like interacting with the ground. So the force of, what should we call that? I guess we could say it's like pushing. It's like a horse pushing off the ground. The force of push on the horse from the ground. You could say, like, I've had students in the past call that the force of trot or something like that. That's all fine. I'm not going to fuss at you about that. Every once in a while, it's a little bit tricky to get some of those details, and that is really not what I'm interested in giving you a hard time about. All right, so I think we did this. What is a possible numerical value for how hard the cart pulls back on the horse? How hard the cart pulls on the horse? It's got to be 75 newtons only. Because of Newton's third law. Right? Equal opposite. So there's only one force there. This and this is actually the same force. This is how the cart experiences it, and this is how the horse experiences it. But it is the same force. What is a possible numerical value for the forward force on the horse? It's got to be greater than 75 newtons. Oh, no, sorry. Wait. What is a possible numerical value for the forward force? Oh, on the horse, sorry. Yes, it's got to be greater than 75 because accelerating forward. What is a possible numerical value for the friction force on the cart? The friction force on the cart has to be less than 75 newtons because, same reason, because it's accelerating forward. So it's got to be less than that. Explain how Newton's first and third laws are represented in your previous answers. Newton's first law is just things keep doing what they're doing. Newton's first law, we could say, there's no motion in the up-down direction, so that's how we knew that those forces were balanced. We could use, that's an example of Newton's first law that's happening here. Vertical forces are balanced because no vertical motion. And then Newton's third, we have the force of pull on the, let's do cart first, cart from the horse, and the force of pull on the horse from the cart. Those two are a Newton's third law pair. And that deserves an exclamation point. All right. How about this? To the left of the picture. Sorry, that's just going to do them right here. We don't have another picture. So this time we're going at a constant velocity. Change up the masses a little bit on you. So how does that change things? Not much. It just makes that force of gravity on the cart from the entire Earth equal to 2,000 newtons. The support force on the cart from the ground, also 2,000 newtons. The pull force is 100 newtons. If you're looking at this and thinking like, oh my goodness, like look at your scale here. This is supposed to be 2,000 and this is supposed to be 100. That should be like 20 times smaller than that. As long as you have the numbers there, then it's all good. Let's see. And this, we're going to get a constant velocity now, so forces are balanced, so that force of friction now has to be equal to that. And here, on the horsey, I've got force of gravity on the horse, the support force. So this is where you can make the joke, like what is the source of the force on the horse? Well, here for the normal force, it's the ground. And those are 2,500, 1,000, 2,500. Just kidding, 2,500. I know how to say numbers. And if this is the force of pull on the cart from the horse, then the force of pull on the horse from the cart, that's the Newton's third law pair. So I'm going to use those two tick marks, and I know that that must be equal to 100, because that is the same force. And furthermore, since we're going at constant velocity here, sorry, I didn't mean to cross that out, just to emphasize it, this force of, what did we call it? The push on the horse from the ground also has to be 100. Because the forces here are balanced too, because we're going at a constant velocity. So what's the numerical value for how hard the cart pulls on the horse? 100. Because Newton's third law. What is the numerical value for the forward force on the horse? 100. Because why? Because Newton's third again? No, because Newton's first law. Because the forces are balanced. And why is it Newton's first law? Because constant velocity means balanced forces. What's the numerical value for friction? 100 newtons, because Boy, I'm teaching you to be lazy here, huh? I'm going to write it again. Because Newton's first law. Constant velocity, balanced forces. Explain how Newton's first and third law are represented in our previous answers. I think that we pretty much did that. How about C number 7 through 9? Oh dear, this is really not good for me to teach you to be lazy like this. Oh well.